Howdy! The purpose of this video is to describe one principal kind of a linear defect, and that is a screw dislocation. Now, there are two kinds of linear defects that we've talked about so far, edge dislocations and screw dislocations. Edge dislocations occur when you have an extra half a plane of atoms in the lattice. Screw dislocation is very different. Instead of having an extra half a plane, the lattice itself is sheared, so part of that lattice is offset by a bit relative to the other part of the lattice. It gets its name a screw dislocation because if we start at one point on the crystal lattice and we walk a path around, we end up immediately below that point. And if we continued to do that, we would end up below that point again, and so on and so forth. So it follows the helical path of a screw. Now, let's do similarly to what we did for the edge dislocations. Let's first start by describing the Burger's vector for the screw dislocation. So if you remember, a Burger's vector is a vector that completes a circuit that is drawn around that dislocation. So in this case, the dislocation, again, it's a linear dislocation, and it extends into the lattice this way. So we see, again, there's a plane of atoms that has been sheared so that the top half of this volume along that plane was sheared sort of back and to the right. This illustration below, in this illustration below, we're looking down and we're looking down on that plane itself. And so you see there's some region where we're drawing shear, and by the time we get over here, all of those, the top lattice has been sheared one unit cell off to the right. So the dislocation itself is the line. Let's change colors. The dislocation itself is the line that is defining the edge of this plane of shear. So the Burger's vector, again, we're going to follow a convention. We're going to follow a right-hand start-to-finish convention. Just like with the edge dislocations, the specific convention you use is not as important as is the fact that you maintain the same convention throughout. Okay, so if I use the right-hand rule, I align my thumb along this this screw dislocation. I've given it a direction here, so that's a sense vector. If I align my thumb along that, then I'm going to follow a path that goes in that direction. So let's start, let's say I start here. And let's try and make a loop that's about 4 unit cells on the side. So I'll start by going down 2. I'll go over 4. 1, 2, 3, 4. I'll go up 4. 1, 2, 3, 4. I'll go to the right 4. 1, 2, 3, 4. And then I'll go down 2. 1, 2. So if there was no dislocation there, I would have 4 unit cells on a side. It would be a loop, and I would come back to the same place. But now you can tell my start point here is different from my finish point here. And so again, I draw a vector that goes from the start to the finish, and that vector is the Burger's vector. It's hard to see it just because I've drawn it so small, but it's 1 unit cell in that direction. And again, I use the symbol B to denote the Burger's vector. Okay, so as opposed to the edge dislocation, for the screw dislocation, the Burger's vector is parallel to the dislocation itself. So the line of the dislocation is this line, and the Burger's vector is this vector here. Those two are parallel. In edge dislocations, those two are perpendicular. Okay, let's talk about stress fields. So in screw dislocations, a screw dislocation is a pure shear dislocation. What that means is there are no regions of compression or tension. It's purely shear. I mean, we can see this if we are looking at the projection down, for example. We're looking at one specific plane, and we see shear between the top and bottom plane. But in reality, that shear sort of decreases radially away from the dislocation itself. So remember, the dislocation is a line, and the shear will decrease radially away from the line. So screw dislocation is pure shear. Okay, finally we're going to talk about dislocation motion. And so again, we're going to apply some shear force to this volume. So if I'm shearing the top half in this direction and the bottom half in this direction, the question is, how is that dislocation going to move? And again, there are a couple of different ways to think about this, but the way that I tend to think about this is the net effect is that this whole top half is going to want to move that way relative to the bottom half. And so if I have my dislocation here, I can see that right side, I've already been offset by 1 unit cell. And so if this dislocation moves 1 unit cell to the left, then I've now offset a little bit more of the volume. And so what happens is, as I apply this shear, the screw dislocation actually travels. It looks like it's from right to left in this illustration. So it'd start in the middle and it would move. So it's here and then here and then here, and then it's out of the volume. And the net effect is that after that happens, I now have, oh, that's a terrible drawing. I now have a volume that is entirely offset by 1 unit cell. And so if I had another screw dislocation pass through that volume, again moving from right to left, it would be offset an additional unit cell. So what does this mean? If I have a particular direction of shear, then the dislocation is going to move perpendicular to that direction of shear. And furthermore, that direction of motion is also perpendicular to the Burgers vector.